So, hello and welcome. My name is Tom Bridges. I am broadcasting from the University of Surrey in England, where summer has finally arrived and we can throw off the sweaters we were wearing for most of August. It is a pleasure to welcome you to the first SIAM webinar of the new academic year. Our speaker is Chris Jones. He is a research professor and professor emeritus at UNC Chapel Hill, an affiliate professor in mathematics at George Mason University, a professor of meteorology and visiting professor of mathematics at the University of Reading in the UK. 2023 is the 35th anniversary of the publication of Chris's seminal paper on the Maslov Index. It was published in December 1988 in the Charles Conley Memorial Volume. The paper was on the stability of standing waves of the NLS equation with variable coefficients. It was this paper which first caught my attention in the early 1990s when I was a postdoc at the University of Utrecht. It was the first time I heard the name Chris Jones. It was the first time I heard of the Maslov Index, and it was the first time I saw the use of differential forms in the context of nonlinear waves. This paper influenced me and was widely influential. I first met Chris Jones in person in the 1990s when we were both at the University of Stuttgart. Chris was a Humboldt Prize winner, and I was a Humboldt Fellow. It was a fantastic opportunity to be exposed to Chris's overarching geometric approach to dynamical systems and wave stability problems. I will just mention one highlight. Chris gave a series of lectures on Das Austauschlemma, which were remarkable on two fronts. They were given in German when he was neither a native speaker nor formally trained, and exposed all of us to the details of the exchange lemma, a beautiful combination of geometric singular perturbation theory and the theory of differential forms. In the past 35 years, Chris has shown the Maslov Index to be a major paradigm in the analysis of nonlinear waves. This program has influenced or involved collaboration with a wide range of mathematicians, including Baird, Beck, Bose, Sardard, Chen, Cornwell, Cox, Deng, Howard, Hugh, Batushkin, Malham, Marangel, Suktayev, and many others, as well as myself. Three important new directions in this program are the extension of the Maslov Index to elliptic PDEs, abstract results for gradient reaction diffusion equations, and generalization of the Maslov Index to non-Hamiltonian systems. It is this latter paper that is the impetus for this talk. It was published in SIAM in 2022. It is a remarkable paper in that it combines symplectic topology with dynamical systems to generalize not only the Maslov Index, but also the concept of Lagrangian Grassmannian, all applied to nonlinear waves. That paper is the starting point for this talk, although Chris has enlarged the theme to stability indices for nonlinear waves and patterns. So without further ado, I will turn over the virtual floor to Christopher K.R.T. Jones, aka Knight of the Round Table.
Hey, thank you, Tom. A very gracious introduction. I actually thought I would extend the theme, and then I thought I would narrow it again. So I am actually going to focus on that paper because I realized doing something more was too ambitious, and I was too tempted to really try to explain the ideas and the origin of the ideas rather than, give a big general overview where I talk about the Evans function and so on too. So that paper, my collaborators on that paper are Tom Baird from Memorial University of Newfoundland, Paul Cornwell, who is a grad student of mine, Graham Cox, who is also at Memorial University, Robbie Marangel from the University of Sydney in Australia. What I want to do though is give particular thanks to Beers, because it was Beers that the Banff research station which really allowed us to develop this idea. Graham and I were sort of pushing to try to extend the Maslov Index, but we kept hitting our heads against a brick wall. And so we engaged algebraic topologists, and that was Tom Baird and Robbie Marangel, and it was really this FRG meeting in Bears in 2018 that really managed to make progress and do something. And what I want to hope I explained today is that it's not really as complicated as it sounds. Okay, first of all, this is you know, when I was a kid, I used to see this show called This Is Your Life. I don't know how many people here are old enough to remember that. Remembering the American one, I think, is harder because it was the original one, and I remember the British one, which was sooner. But I figured, you know, This Is Your Life, they bring in people that you knew growing up. You know, here's your kindergarten teacher and stuff like that. I thought a mathematician's equivalent to this was bringing in all the equations you've ever worked on. So, like, this is the first equation that you worked on. So I would say most of my thinking is revolved around these 4 types of equations. One, a basic reaction diffusion equation, then the nonlinear Schrodinger equation, nerve impulse equations like the Fitch-Nagumo equations, and then viscous profile equations, where you take conservation laws and you add viscosities. And I've spent a lot of my life looking at traveling wave, standing wave, steady solutions of these equations and asking questions about stability. So the idea is to ask questions about stability to perturbations in initial conditions. You have a wave, you have a pattern, you perturb it a little bit in the initial condition. Does the resulting solution settle down to the wave, some translate of the wave, or whatever? The main strategy for considering that, which is now time-tested over centuries, is to linearize at the base state and look at an associated linear problem. PT is equal to, let's call it LP, and then look at the spectrum of this operator L. If the real part of the spectrum is all in the closed left half plane, then you have stability information contained in that. I'm not saying you have stability because there are subtle points which certainly everyone in PDEs would be attuned to in moving from the spectrum to actual full stability of the thing, including a sort of spectral mapping type theorem and then estimates in controlling the nonlinear terms. That's also something that's extremely interesting, but I'm going to focus on the spectral information and the linearization because it's where a lot of the phenomena are. And it's also true that if you look at it sort of from the instability point of view rather than the stability point of view, namely you want to find instabilities, then as long as you have the real part of lambda bigger than 0, it's pretty unambiguous that you have instability. So that's going to be the context. And here again is the paper which was picked out as motivation for this talk, and that Tom mentioned, which appeared in SIAM in 2022. Let's see, the underlying philosophy of this whole thing is to find an index. In this case, we're looking at an index for counting positive real eigenvalues that correspond to wave or pattern instabilities. And to somehow relate that count to the structure of the wave or pattern itself. This is not to say that I have some magic bullet that says that there should never be complex eigenvalues. Of course, if it's a self-adjoint problem, there are no non-real complex eigenvalues, and that's a nice case. But still, one can ask the question about actually how do you count positive real eigenvalues, even in the presence of non-real eigenvalues. And of course, a lot of the bifurcation phenomena and the onset of instability phenomena correspond to real eigenvalues passing through 0. So Sturm-Liouville theory is the classic example of this, and much of our work is motivated by Sturm-Liouville theory. So I will explain that in some detail, our view of it, and how it was sort of generalized in this program. So in this case, then you get the number of zeros of something, usually the derivative of the wave or pattern, or hopefully something to do with the wave or pattern, will give you the index of the count of the positive real eigenvalues. The Maslov index is thought of as a generalization of Sturm-Liouville theory, where you have an oscillation in the space of Lagrangian planes. The corresponding object on the right that has to do with the structure of the wave or pattern is usually called the number of conjugate points, which is well known in the calculus of variations. And it's exactly the same thing here. So we tried to, we always tried, you know, the Sturm-Liouville theory only works for second order equations, and Maslov index generalizes it to higher dimensional systems where you have systems of more than one equation. But it requires something, namely the eigenvalue problem that emerges has to be Hamiltonian or can be transformed to a Hamiltonian. And the Maslov index works because of the topology of the so-called Lagrangian Grassmann. I hope that will come out, and I'll explain that a bit. So our idea all along, which Graham Cox and I pushed for many years, was to try to fatten up the Lagrangian Grassmannian. It is a submanifold of the usual Grassmannian, and the idea was to sort of fatten it up to accommodate more systems. The Hamiltonian structure meant your relevant trajectories stayed in the Lagrangian Grassmannian, and the hope was that we could actually get things to stay in something that was slightly bigger and loosen up the constraints on the equations. This turned out to be wrong, and we were led to something else, which is kind of a generalization, but it's also a little bit different. But the idea of fattening up the Lagrangian Grassmannian was probably basically the wrong idea. And we were led to something which we call the hyperplane index. And what I want to show you is that in some ways, the hyperplane index is a closer generalization of Sturm-Liouville theory than the Maslov index is itself. I'm not going to emphasize the piece of the puzzle about the structure of the wave, maybe to the disappointment of many people here, because that's sort of where the PDE interest perhaps lies. But what I want to get across is the ideas underlying this hyperplane index, and also show how crucial it was for the algebraic topologists to be involved and to sort of lead us in the right direction. Okay, so let's look at a basic reaction diffusion equation. So I've got ut is duxx plus f of u. On some domain, I could think of a bounded domain, which is what I will largely do with, say, Dirichlet boundary conditions or Neumann boundary conditions, or I could look on the whole real line in a suitable space. I then look for a steady state solution. Let's call that a pattern. I linearize at that base solution, and that's my linear operator. The spectrum is the set of complex numbers so that L minus lambda I does not have a bounded inverse, which is perhaps a definition that we all know and requires actually the specification of a space, but those who work in the area know that this is actually notoriously insensitive to the actual space you use. The space generally will tell you more about what type of spectrum according to sort of definitions of subsets of the spectrum you are looking at. So of interest then is going to be the instability question, is finding lambdas in the spectrum of L for which the real part of lambda is positive, which corresponds to instability of the U tilde relative to perturbations in initial conditions of the equation up there. Okay, so what I want to do is first give a geometric view of Sturm-Liouville theory. So this is nothing new, but it motivates what we do, and I think it shows kind of where it comes from and how we thought of it. So this is the scalar case. P is just in R, a real scalar. The operator is LP is Pxx plus df of u tilde. I'm taking d is equal to 0 now for convenience. I write that as a system of equations. P prime is q, and q prime is lambda minus df of u tilde times p, right? And notice that that has a nice sort of special structure. There are no first order terms in that. There could be if we were looking at traveling wave problems, and that doesn't impact Sturm-Liouville theory. What you want to do is find a lambda so that that can be solved with boundary conditions. Let's say we're looking with Dirichlet boundary conditions and we're on 0L. Then we'll take P of 0 equals P of L is equal to 0. All right, so the way to think of this is to think of the horizontal axis here is the x-axis crossing the domain from 0 to L. And P and Q are the variables of the phase space. And if you're starting with P of 0 is equal to 0, then you want to start a solution on the vertical axis, right? So it only has a Q coordinate. The fact is that if you have a solution, then you multiply it by scalar, you also get a solution. So you might as well take actually any point on that vertical axis, and indeed perhaps take the entire subspace and flow that entire subspace, and that will actually spawn as it moves along in X a one-dimensional subspace for each X. I'm thinking of lambda as fixed now, right? And then when you get towards the end, you want to satisfy the right-hand boundary condition. You want to find a lambda where you satisfy the right-hand boundary condition, which means that your the thing that you're following here, the object that you're following, matches up again with P is equal to 0. Okay, so that's sort of the basic picture to keep in mind. Let's extract a little bit of that and name the vertical axis in the PQ plane as the Dirichlet subspace. We'll call that XD, and give a name W minus X lambda to the thing that emerges from that we're going to use as our test for finding an eigenvalue when it gets to the right. So the defining condition of W minus as a function of X lambda is that when X is equal to 0, it's equal to XD. And this is always a one-dimensional subspace of R2 for each X and lambda. Okay, so that's sort of that's a key. And lambda is an eigenvalue if and only if you intersect XD non-trivially. It would always intersect in 0 when you get to X is equal to L. So in these dimensions, that happens if and only if W minus of L lambda is equal to XD. That's the only way, because they're both one-dimensional spaces. Okay, that's not going to be true in high dimensions, and that's a key. So the basic idea of Sturm oscillation theory is to exploit the fact that this W minus is a one-dimensional subspace. You can therefore think of it as an element of the one-dimensional projective space, which is essentially the circle. And what you want to think of here is just the one-dimensional subspace swinging around. So I got it here marked at x1, and it swings around and marks to x2. So it's the spinning of this one-dimensional subspace, which is measured in S1, that is the foundation of Sturm oscillation theory. And we could also represent it here, and that may be a lot simpler and clearer, but doesn't generalize quite as easily. We could represent this W minus, this subspace, by the angle the subspace makes with an axis, for instance, the P axis. Then you could say theta is the arctan of Q over P. You can calculate an equation for theta, and that's usually how Sturm-Liouville theory proofs work. if you do a calculation of the system in P and Q, the two-dimensional system in polar coordinates, then the theta separates from the radial system, and then you just have an equation for theta. It's rotation of the angle, and all the spinning in projective space are equivalent that lie at the bottom of Sturm-Liouville theory. So rotation can be measured by an intersection number with the vertical. Right? So number of times you go through the vertical. So there's a duality in topology between rotation and intersection. And it's that duality that is absolutely critical to making everything work. So the intersection number with the vertical would correspond to a value of x, say A, where P is equal to 0, right? So that's P of A lambda is equal to 0. So what we would want is the W minus, which is defined to be at 0 lambda to be 0 to hit the vertical at x is equal to L to hit this P is equal to 0. Now, a key point here is this is not the way it's expressed in Sturm oscillation theory, but this is exactly the same as saying that there would be a solution to the boundary value problem on a smaller interval, namely 0 to A. And that is the notion of a conjugate point. That's the definition of a conjugate point, which does generalize to higher dimensional systems. Okay, but how do you actually use this to find eigenvalues? Well, if you want to find these eigenvalues, then one way to look at it is to take a box. And here I'm looking for eigenvalues between lambda 1 and lambda 2. And I've got two variables, W minus of X and L. Okay, and the way I'm going to think of it is that I'm going to think of considering this whole box and thinking of W minus as a function of X and L. And then I'll think about going all the way around this box here and looking at the sum of the indices, which is the rotation index that you define by looking at this as a curve in projective space or looking at the angle. And you observe that you have to have the sum of those two things. Notice that I put the last two here with a minus sign in front because they're sort of going backwards from the first one. But the sum of those four indices is going to equal 0, right? And that's because what you're doing is mapping the entire rectangle into RP1, but that means that the curve around the boundary is contractible within RP1, which means the index is going to have to be 0. So the rotation around the outside is net 0. So if I set I4, however, has to be equal to 0. That's because basically I4 is all you're looking at here. That's W minus of 0 lambda as lambda varies, but that's always XD. So that's just a constant space, so there's no rotation there, which means that I2 is equal to I3 minus I1, right? So I2 is somehow the difference between this, if it were going in the other direction, and this, right? But I3 and I1 basically measure the rotation of the solutions at that fixed lambda from X going from 0 to L. So I got a cute little graphic here. You can see, I'm assuming on the left that rotates around 3 times, okay? So it's 1, 2, 3 times, or 3 crossings with the top, like a double spin. And on the right, I'll assume that it just goes around for a half spin, which means that it just comes back and intersects once. So there's just that eigenvalue there at lambda 2. So that means you've gone from I3 equals 1 to I1 is equal to 3, which implies by Sturm-Liouville theory that there have to be 2 eigenvalues in here. This actually comes out, the number I2 comes out as minus 2, but you somehow count them backwards. let's iterate that. So this I2 here, what happens along this I2, this is X is fixed at L. What happens along that I2 is basically you're looking at the rotation of W minus evaluated X equals L as lambda varies. And you want that to hit XD. So you're rotating around looking at the number of intersections with XD. Well, each intersection with XD is an eigenvalue. So that's how I2 counts eigenvalues. Okay, what if you actually wanted to do stability out of this? Well, then what you would do is you would take lambda 1 is equal to 0, and you would take lambda 2 very, very large. If you take lambda 2 very large, you see that the lambda actually swamps the equation. So in fact, nothing happens on this side here. So that means in that case, sorry, this is lambda 1 equals, yeah, lambda 2 bigger. In that case, then what you see is I3 equals I4 is equal to 0, right? You may again have something on the left here with some rotation inside here, which actually is going to correspond to the number of zeros of the solution of the 0 eigenvalue problem. And then you're going to have lambda 2 very large. So you're counting the number of eigenvalues by looking at the index along this top shelf here, the number of eigenvalues between 0 and essentially infinity, because you've got to the point where there are going to be no more. Okay, so the number of positive eigenvalues as a result of this is equal to the number of zeros of W minus X0, which is the solution when lambda is equal to 0. And in classical application of classical Sturm oscillation theory, you relate that usually to the number of zeros of the derivative of the solution, because that also satisfies this equation, the same lambda equals 0 equation. It doesn't satisfy the boundary condition, so there's a little bit of work to finesse that. As I said, I'm not going to go into that side of things. But the upshot is that you look around this box here, the rotation around the entire outside is net 0 count. On the right shelf and the bottom shelf, there's no rotation. Therefore, the rotation along the top shelf is equal to that along the left shelf. That along the left shelf is something to do with the solution of the lambda equals 0 eigenvalue problem, which may be related to the original wave or pattern. And along the top shelf, it's the number of positive eigenvalues counted made. Okay, we can think of W minus as a flow in either variable. So in X, it's called, you might call it the dynamical flow. You fix lambda, let X vary, then this is a flow in X. In lambda, you could also think of it flowing. You fix X and you let lambda vary, and that's called spectral flow. So that's a term you may have heard in connection with Morse theory and other things like that, but that's basically what it is. You could fix lambda and go vertically and you'd be doing dynamical flow. You could fix X and go horizontally and you'd be doing spectral flow. And you can do that in the whole neighborhood. So we can think of it as a flow in either variable or as a sort of double flow in both variables. What I want to ask here is, what are the lessons from Sturm-Liouville theory about what we might hope to try to generalize? What are the ingredients that make this work that we would have to generalize to higher dimensions? So the first thing is that there's a rotation index, right? There's some kind of rotation here. We've got an underlying sort of projection, if you will, onto a circle, and that gives us some sort of rotation. The second thing is that we have to relate the rotation to intersection with a boundary condition subspace. That's obviously critical because that sort of allows us to say the rotation index counts eigenvalues. But we also need to have continuity in X and lambda. That's this sort of double flow here. And what we have used here implicitly, or I haven't really emphasized, is monotonicity in X and lambda. That means that if you let X and X vary, you look at the dynamical flow, you cross the vertical only in one direction. It's also true that if you look at the lambda flow, the spectral flow, you cross the vertical only in one direction. That means that by getting this rotation, you get an exact count of the number of eigenvalues. So the rotation index and the intersection have to do with the ambient space being the real projective space. From a topological point of view, I mean, we think of it in terms of the angle and the circle and stuff like that, but from a topological point of view, it's because the real projective space has fundamental group Z. It has a rotation index. The continuity in X and lambda, as I said, has to do with the double flow here. The monotonicity is a nice thing to have because it gives you an exact count. But in some sense, it's kind of optional. Suppose you want to have a lower bound on numbers of eigenvalues. So you want to answer the question, is there an instability? I don't care how extensive that instability is there just an instability? Then you don't worry so much about monotonicity in X and lambda. And in fact, that's one thing that we, to some extent, give up. There's also another special thing in these dimensions, and that is that eigenvalues are always simple. Okay, they always have geometric multiplicity equal to 1, just because of the dimensions of the intersections. And that's something we lose too, which is a bit related to monotonicity, but not completely. Okay, so now let's try to generalize Sturm-Liouville theory to systems. So let's take our PDE back here. UT is UXX plus F of U, but I'm going to take U now to be an Rn. So U is a system, okay? I'll work on the same bounded domain, 0L. I'll implicitly think of Dirichlet boundary conditions. I get this system now of equations. P prime is Q, Q prime is blah, blah, the same thing, but that's now on R2n, right? XD is going to be an n-dimensional space, and W minus of X lambda, which is defined by taking all the initial conditions on XD and letting them flow, is an n-dimensional subspace of R2n. So we had real projective space RP1 because we had one-dimensional subspaces of R2. We now have n-dimensional subspaces of R2n. So the appropriate object to talk about then is Gn of R2n. That is the Grassmannian of n-dimensional subspaces of R2n, right? And that cannot be avoided in trying to talk about index theory for these things and getting stability indices, so on. It's the natural space to be looking at these things in, this double flow in, is Gn of R2n. And that you can show that you get, again, this sort of double flow in this situation on the Grassmannian of n-dimensional subspaces of R2n. That's actually a well-studied object in topology and geometry, and Gn of R2n is well understood as a space, or as actually as a manifold. But there's a dimension change here. Gn of R2n is bigger dimensional. It's actually 2n choose n choose 2n, 2n choose m, I think, right? So of dimension. So it can get very big, which is partly problematic. In the dimensions we're interested in, usually it's okay. The problem is, though, the key problem is that the fundamental group of the Grassmannian is actually Z2 and not Z. So you get no rotation. you often see theorems about the parity of numbers of eigenvalues, of positive eigenvalues in stability problems. That, I think, has its root in the fact that Z2, just the group of two elements, 0 and 1, is the fundamental group of the Grassmann. Okay, so what's the first thing a mathematician does when confronted with this is, well, make a definition, right? So that's actually the last thing we did, but it sort of works to think of it logically as the first thing. And we define these things called Maslov spaces. So this is in this paper. This is one of the key points of the paper, although it's particular Maslov spaces that give the hyperplane index, which I want to spend most of the rest of the time explaining. But Maslov spaces then are subspaces or subsets of Gn of R2n. Okay, and what you're going to think of actually is that there are three objects involved. There's the main space M, which is our thing that's going to replace RP1. There's going to be a fixed subspace X, which is in Gn of R2n, which is going to be the thing that we may intersect. It's going to be the intersection subspace, so the equivalent of the vertical in the Stern oscillation thing. And there's going to be a cohomology class of infinite order in the first cohomology class of M with coefficients in Z, right? So cohomology just means something that you would apply to something in H lower one in homology, which is essentially curves, closed curves. So this is something that you evaluate on closed curves and gives you a number in Z. So this is the rotation index. It's this cohomology class. And the idea is it's going to be related, the rotation using this cohomology class is going to be related to the intersection with the fixed subspace. And the fixed subspace is going to be related to the boundary condition. So Dirichlet means it would be P equals 0. That's an n-dimensional subspace of R2n. Neumann Q equals 0. Again, an n-dimensional subspace. Okay, so that's kind of how this is going to go. We're taking the ingredients in Stern-Liouville theory and saying a Maslov-Arnold space is going to be a subspace of Gn of R2n, which gives us those properties that allowed the Stern oscillation theory strategy to work. But intersection is not so straightforward in high dimensions. I alluded to that earlier. So if you look again at this picture here of our sort of initializing space at x equals 0, spawning this W minus of x lambda, which is this curve of n-dimensional subspaces, to have an eigenvalue is not necessarily to match up exactly with P is equal to 0. So the problem is that W intersect X, say XD, is not necessarily n-dimensional. What it would be if it matched up entirely with P equals 0. It could be 1, 2, up to n-dimensional, right? And in fact, generically, if you think about it, it's going to be one-dimensional, right? If you sort of move them around, you should perturb them around, it should be one-dimensional. So this leads to this definition here, which is a standard definition in the study of Grassmannians, is to look at the set of subspaces that intersect your given space X non-trivial. And that's usually called the train of X. That's the terminology used for it. So this is a really important subset of the Grassmannian. Given a particular X is the train of X. And if you think about it, what we're going to do is look for intersections with the train of X. Okay? So now let's see how do we look at eigenvalues of L with Dirichlet boundary conditions. So lambda is an eigenvalue of L if evaluated X equals L, it intersects with XD non-trivial, because then there will be a solution which satisfies boundary conditions at both ends. At the left end, by virtue of its being in W minus of X lambda, and at the right end, because when you evaluate W minus at X is equal to L, it non-trivially intersects XD. So that allows you to pick something out of that, go backward in time, that's the solution. But that is actually equivalent to W minus at L at lambda is an element of the train of XD, right? That's the key observation and the key use of this set, the train, is that intersecting XD is the same as the space in the Grassmannian intersecting being an element of the train. In other words, intersecting the train. So this W minus of X lambda intersects the train when you get to lambda, X is equal to L. All right, so armed with a Maslov-Arnold space, how would a Sturm-Liouville theory type argument go? Well, you would take lambda is lambda 1, lambda equals lambda 2 are eigenvalues, and then set the two curves, one at the lambda 1 end and one at the lambda 2 end, and assume that those are eigenvalues, look at those two curves, and then evaluate the cohomology class alpha on those two curves. If those are not equal, then there is an eigenvalue in between. This is how it would go. Because the cohomology class is related to intersection with the train of XD, right? And XD would be the subspace you would take in your Maslov-Arnold space. In fact, there are at least as many as alpha C1 minus alpha C2, right? So this is here we're talking about the sort of lower bound here. Actually, the Maslov-Arnold space does not guarantee an exact count, even if you have monotonicity. That's an interesting point. So caveats to all this. How do we know that there are any Maslov-Arnold spaces at all? If we have a Maslov-Arnold space M, we have to make the argument that W minus of X lambda actually lives in M for everything in our box here, which actually, incidentally, we call the Maslov box because it was sort of, this way of looking at it was honed using in the context of the Maslov index, right? So this whole thing has to get mapped under W minus into M, this Maslov-Arnold subspace of Gn of R2n. We call this, and this has to be continuous, right? We call this an invariance condition because it's sort of invariance. It means that this set M is invariant under the double flow, W minus of X and lambda. But this is a strong thing to require. But let's first of all answer the question, are there any Maslov-Arnold spaces? Well, the Maslov index itself gives you a Maslov-Arnold space. And how does that go? Well, the Maslov index is, as I indicated in the beginning, concerns Hamiltonian systems. So you take a symplectic form on R2n, which is a non-degenerate 2 form, right? And if it's a Hamiltonian system, it preserves that omega, and that's at the heart of this. The main example would be omega of UV is U, the inner product of U and JV, where U is that usual sort of symplectic type matrix, 0 identity minus identity 0. That's the standard, that gives the standard Hamiltonian structure on R2n that we all know from Newton's laws of motion. So lambda of n now is the set of subspaces in Gn of R2n on which omega vanishes. And that, as a subspace of Gn R2n, is invariant relative to a Hamiltonian system if you have it. That's called the Lagrangian Grassmannian, or when n equals 2, the space of the Lagrangian planes. I listed down here a bunch of authors who used the Maslov index, worked on it. These people were, I think, pretty much all mentioned by Tom, but I also included Arnold, who was the one who really started this connection I think, with differential equations, and he showed how you could get the Morse index theorem out of the Maslov index in a beautiful paper in 1967. So facts are the following. Lambda of n is a Maslov-Arnold space, and the alpha is called the Maslov index. You can actually sort of define the rotation. There's a natural cohomology class in the space of Lagrangian planes. And of course, among other possibilities, we can take the intersection space, Maslov-Arnold space, to be either the Dirichlet subspace or the Neumann subspace. Well, how does Maslov and RDE go? Well, you have an equation like this, and you want to ask, well, when is this system Hamiltonian over here? It's set up to be Hamiltonian, but there's a big extra constraint, namely that this nonlinear term f of u has to be the gradient of a function. So that means that you're talking about gradient systems, and that's the big constraint. So our aim was always to generalize the Maslov, the Lagrangian-Grassmannian by finding a Maslov-Arnold space so that the Lagrangian-Grassmannian was a subspace of it. But it was easier for equations to stay within M. In other words, fewer conditions on the nonlinearities F. You didn't want it to have to be a gradient. Okay, but in this paper, one of the theorems we prove is that you can't do that, at least not nicely. There is no extension of lambda of n that is a connected, smoothly embedded submanifold of Gn of R2n. Right, so that's sort of a non-existence theorem of our ability to do this. You can find a fattened up version of the Lagrangian-Grassmannian, which we call the fat Lagrangian-Grassmannian, but it has a singularity in it. It has a place where it gets very, very thin. It's not a nice submanifold. We know that these are not, we want them to be open submanifolds because we want them so non-compact. We want them to contain as much of Gn of R2n as we possibly can. But we did want them to have consistent dimension across the whole thing, rather than there being a bottleneck that you have to travel through. So the theorem here is that there has to be a bottleneck. So we came up with this idea called the hyperplane index, and it goes as follows. And as I say, what I want you to think of is that this is, in some sense, a more natural generalization of Sturm-Liouville theory than the Maslov index is. I think one of the blocks in this, we always say that the Maslov index generalizes Sturm-Liouville theory, but it's really hard to sort of see that because it looks like a different object. This doesn't. So we're going to take omega to be a non-zero n form on R2n, and let H omega be a hyperplane in Gn of R2n on which omega vanishes. So H omega is the span then of n vectors, which have to be linearly independent in Gn of R2n. And what we're going to require then is that omega is zero, those vectors. So that's on which omega vanishes. And then we're going to define a Maslov-Arnold space using two hyperplanes. So the hyperplane Maslov-Arnold space, it's a hyperplane because it's given by one condition here, right? So a hyperplane Maslov-Arnold space is a subset of Gn of R2n. We're not saying it's a subspace because that's too grand for this. It's, in a sense, it's quite a crude object. Is Gn of R2n take away the intersection of two hyperplanes, where we require that omega and omega 1 be linearly independent, right? So we're extracting from the Grassmannian two hyperplanes, right? And we're going to require, though, that one of them has kernel of omega 1 n-dimensional. It turns out then, if the kernel of omega is n-dimensional, the hyperplane is actually the train of the kernel of omega, right? So this is where one of our things here is going to give us one of our hyperplanes is going to give us the intersection space. right? Because it's going to be the train of the kernel of omega. Notice, though, that we're crossing out. We're taking it out of the space. You would think that we would want it to be in the space, right? But we're actually taking it out of the space. If you think about it, it's only a piece of the train that you're taking out of the space. And you do that in the Sturm-Liouville theory too, because you take the origin out. It's not the entire subspace that's in there. Okay, so let's see, why should this have a sort of oscillation in it? Well, think about it. Think about n is equal to 2. G2 of R4 is actually a 4-dimensional manifold, and you would be taking out two-dimensional sort of hyperplanes, like linear things inside this 4-dimensional thing. You're taking the intersection of two-dimensional things out. And if you think about it, that does give you sort of an oscillation, right? But we got to figure out what that is. So what is the rotation in the hyperplane of the Maslov index space? And here's where you sort of see it looking like Sturm-Liouville theory. So we're going to define a map from this hyperplane space, the hyperplane map, MA space, into RP1, one-dimensional real projective space, by taking the subspace spanned by omega 1 of a spanning vector for the subspace X and omega 2 of a spanning basis of the space X. Okay, so phi is well defined because these are not simultaneously 0 in M. That's the reason for extracting, right? It's that sort of simple. Then you can do this. Right? We could also have defined this by an angle. We could have taken the arctan of omega 2 over omega 1. So there it's starting to look exactly like Sturm-Liouville theory. So here's the analogy with Sturm-Liouville theory. Here's your Maslov-Arnold space, Gn of R2n, take away the intersection of these two hyperplanes spaces. And you're sort of, you want to think of this W minus hopefully is moving around in this M space, but then you can project that down onto one-dimensional real projective space, which is topologically the same as the circle, as we've already seen. And you can basically look at the angle in there. So that means you can measure rotation here in the omega 1, omega 2 space. That's what we're doing. So as long as you avoid those two hyperplanes, you have some oscillation. Okay, how do we choose these two forms? Well, that's obviously the key, right? You've got to, in each situation, you have to choose them in some logical way. Well, one of them, remember we said we're taking one of them to have an n-dimensional kernel, which implied that the hyperplane H sub omega was actually the train of the kernel of that. So that's set up then to choose omega 1, so its kernel is the boundary condition subspace. So for instance, XD, the Dirichlet subspace, or the Neumann subspace, or whatever other thing you want to do. Omega 2, the other one, you're free to choose. And the natural thing to do then is to choose it based on the equations. For instance, we have chosen it in some of the work so that monotonicity across the kernel of omega 1 holds, because this is somehow sort of complementary, right? If we go back to the previous slide, right? You see this in the lower dimensional situation too, right? Sorry, you're crossing, when you're crossing the kernel of omega 1, right? It's you can sort of see something about omega 2 may be related to the direction of crossing. Anyway, that's going to involve. So we want invariance of M under the double flow means that for each X and lambda, either the omega of this object is non-zero or this is non-zero. so we would want to choose that omega-1, omega-2, so that it was invariant. But that's quite difficult. So we've actually, part of the interesting thing here is to open up the possibility of it not being. Well, let's first of all explain how you would do the Maslov Index box view with invariance. So assume that you set up a differential equation, you found your omega-1, you set by the boundary conditions, and you're getting your omega-2 in such a way that the thing is invariant. So this thing lies entirely under the action of the double flow, lies entirely inside M, your Maslov-Arnold space. So the total index around the boundary, I've now used a little h here instead of I because of the hyperplane index. And then sum of those things is equal to 0. So once again, we can take h4 equals 0. And if lambda 2 is very big, we're doing stability here. So we want to take this a long way out. Again, lambda swamps the equations. We can see that h3 will also be 0. So that means that h1 is equal to minus h2. Okay, so h2 is going to count the number of eigenvalues in some way, and h1 is going to be the the hyperplane index, which is you're going to interpret in some way. Well, we can interpret it in terms of conjugate points because we can think of the rotation in the hyperplane Maslov-Arnold space as counting intersection numbers with our boundary condition space, which actually counts conjugate. And H2 is going to count positive eigenvalues. So the theorem that we were able to prove here under these assumptions of invariance is that the number of positive eigenvalues of L is bigger than or equal to the number of conjugate points. This is under the assumption of invariance, though. So, and the interesting thing to think about is perhaps when is invariance not satisfied? So, and we've started to develop a theory of that. It's generically going to happen at just a finite number of points where invariance is going to be lost. In other words, where it's not going to be contained in M. And then what it turns out you can do is you can make a calculation, which is like a winding number around each of these points within the sort of double flow to give you a contribution to the total net winding around the boundary. And we're able to prove the theorem that the number of positive eigenvalues in this case is the number of conjugate points minus n, the total contribution from these points, right? So they can detract from your count here, right? You might think of these as being related to where points go off of the real axis or something like that. They allow points to do that. I mean, we don't fully understand this, but this gives us a direction for looking at in some generality with this, because we can look at places where we actually don't have invariance. Okay, let me finish up. I have not mentioned applications, perhaps much to the disappointment of the audience that I would be thinking of my going back to the original problems, but I'm just going to list some here that we've done. First of all, we have a theorem in the paper that if you take systems with large diffusion and mixed boundary conditions, that's Neumann at one end and Dirichlet at the other, you can verify invariance. That's kind of a sort of interesting, and you can apply this theory and you can get instabilities in that situation. The conditions on large diffusion means there is a diffusion matrix D and the coefficients are big enough, and then there's also a condition on their product. Turing instability, which this sort of large diffusion might make you think of, we can show is exactly related to when invariance fails. That sounds like a really nice result, and it is a really nice result. It's very suggestive, but it's not difficult because you're just talking about homogeneous equilibria. You're not talking about actual waves or patterns with some structure. So But it does turn out when you calculate the boundary of Turing instability, it's exactly when invariance fails. You could show invariance up to that point, not beyond it, with a standard sort of activator inhibitor system, 2 dimensions. Peter Howard, who I mentioned a little earlier, has done 2 very substantial papers, which has various applications of this. He's developed this much further, this hyperplane index, including higher order equations, some with invariance and some without. He explores various challenges in calculating M. These numbers here refer to the papers below, sorry. And he's looked at KDV and KDV burgers. That's quite a substantial paper. So these are the 3 papers, our paper and the 2 papers of Howard, where this hyperplane index has been developed. Okay, that's it. Sorry, tiny bit over. What do I do now? Someone else is.
Well, hello, Chris. If you unshare, maybe we can go back to.
Okay, unshare. So, oh, it's over on my other screen. Oh, share. Okay.
There you go. Right. I think we're back. Yes. Well, thank you very much, Chris. That was a very stimulating talk. And at this point, I think I will open up the floor to questions. And I guess the way we will do this is if anybody signals in the chat that they have a question, then I will free up their mic.
You can also raise your hand. Might be
okay,
easier.
Yeah, right.
So maybe while we do that, I have a quick question, Chris. Wonderful talk. How much of this survives under perturbations?
Sorry, on what?
How much of this survives under perturbation? Can you perturb things a bit? And
yes, it should be, because it's basically topological. It should survive under perturbation, right? I mean, the invariance condition, non-invariance would be closed condition. Invariance would be an open condition, right? Yeah.
I have a question for you, Chris. I thought one of the most intriguing bits was the omega-1 and omega-2.
Right.
In choosing those, and you said one of those could be chosen by the boundary conditions.
Right.
What if you had a situation like solitary waves where you have a boundary condition at -infinity and a boundary condition at +infinity? Could omega-1 and omega-2 be determined by those? Or is it? I didn't quite understand.
That's an interesting suggestion. I hadn't thought of. Yeah, I don't know.
Okay. Yeah. I'm a little bit frightened by the fact that omega-1 and omega-2 can be freely chosen. we do like some more firm guidance on how they can be chosen.
Yeah. Yes, you're right. I mean, it's so that's sort of what is yet to be done, is to figure out how you would choose the omega-2. But but even in the Maslov index, there is this thing that it doesn't matter what subspace you take for the train that you intersect, right? Because if you rotate around once, you intersect the train of every subspace. You intersect the Dirac train, you intersect the Neumann train, you intersect trains of subspaces that may be associated with boundary conditions at -infinity or +infinity. And that's usually kind of a key to how you use the Maslov index, is that's sort of somewhat flexible.
So you think something similar is happening here, where it's not really so important what omega-2 is?
Right. Well, I think that the better thing to do, I don't think you want to, I don't know. It's first I thought of it, actually, now you're saying it, but I don't think you want to tie omega-2 to the boundary. I don't think.
You don't think you want to tie it to boundary conditions?
Not omega-2, omega-1. I mean, one of them you do. It doesn't matter which you call them, but one of them you do, and the other one you want to tie to the structure of the equations. Right. I mean, it's like in the Maslov index, you've got two things. You've got the structure of the equations giving you the Hamiltonian structure gives you the, you know, the rotation thing and the other, and then you have to look at the train, which gives you the boundary conditions.
Okay. Well, you know, in the with the Maslov index, I always associate monotonicity with positive definiteness of the kinetic energy.
Right. Right.
Okay. And so that's a pretty, you know, it's not so often that you have positive definite kinetic energy.
Right.
So I'm, you know, in your case, I guess monotonicity was not as important.
Well, I mean, it's not important. Yeah, well, I mean, no, it isn't important because even I didn't say this, but this hyperplane index does not count the dimension of the intersection. It does not count multiplicity, which the Maslov index does. So that's actually a fundamental difference that is kind of strange in a way. So it doesn't sort of go up when you have higher dimensional intersection. So that, in a sense, already forces you to think in terms of inequalities for the index being bigger than or equal to number of positive eigenvalues rather than equalities. So then, in a sense, monotonicity would be kind of wasted. So because that's generally what you use monotonicity for, is to give you the to give you the exact count rather than an inequality. At least that's how I think of
it. Okay, well, I don't see any other questions in the chat. And if nobody shouts up in the next second or so, I think we'll probably bring this to a close. Anna, do you have any final remarks?
No, except that, of course, we'll have another speaker in a month. And thank you all for attending and participating. And thank you, of course, to Chris for the beautiful talk and Tom for chairing so well.